Hello everyone, this is Panneer from Santhalingam from George Mason University. Today I am going to talk to you about our work on environment independent ASL gesture recognition using 60 GHz millimeter wave signals. We propose a system called mmASL. This work was done in collaboration with Amin, Zhang, Parth, Huzefa from George Mason University and Raja from Calgary University. Let's talk about home assistants. Home assistants are everywhere. They provide us a rich user interface to interact with our everyday devices and make life simple. Most of the current generation home assistant devices are predominantly voice-based. This restricts their access to deaf and hard of hearing community. Close to 500,000 people in the DHS community use American Sign Language, a visual mode of communication for their everyday interaction. American Sign Language involves hand gestures, finger spelling, bodily gestures, and facial movements. Expanding the capability of the current generation home assistant devices to detect ASL gestures will help us to bring the home assistant devices to the DHS community and reap the benefits that we are gaining. Most of the current generation home assistant devices operate in two modes. The first is the wake word mode, wherein the user initiates an interaction with the device, which is followed by the command mode, wherein the user actually interacts with the device. In order to build a DHH home assistant device, we need to solve several challenges. The first one is the ability to detect a visual wake word. In contrast to existing home assistant devices, DHH home assistant devices should be able to detect wake words in a visual mode. The next one is the ability to detect ASL gestures in several practical scenarios. This involves varying lighting conditions, the presence of an interfering user, as well as varying environment conditions. In this work, we propose mmASL, a 60 GHz millimeter wave based DHH home assistant system. 60 GHz signals have been already adopted for the next generation multi-gigabit wireless systems. Because of their higher bandwidth and frequency, 60 GHz millimeter wave signals have also been adopted for several fine-grained gesture recognition systems. The system is built using NA plus SiBeam multi-FPGA software radio platform. Because of their directionality, the 60 GHz systems, in contrast to other RF sensing systems like CSI, are non-intrusive, is tolerant to the presence of other people, as well as environment independent. We propose a custom signal processing pipeline which exploits the observed Doppler spread in recognizing ASL signs using Doppler spread spectrogram. mmASL operates in two phases. The first phase is the wake word recognition phase. In this phase, mmASL detects the wake word and infers the user's intent to interact with mmASL as well as the actual spatial location of the user. mmASL utilizes beam steering to scan the environment and generates a spatial spectrogram. A spatial spectrogram is the concatenation of the different Doppler spread spectrograms generated in each individual beam sector. The spatial spectrogram is further passed down the line to a deep learning algorithm which answers two questions: whether a wake word was present or not, and the actual user location, which is expressed as a beam sector index. With the wake word detection, mmASL fixes the beam sector and moves to the next phase, which is the ASL gesture recognition. In this phase, the user performs different ASL gestures. The raw data, which is recovered from the ASL gestures, is processed using the signal processing pipeline to generate the Doppler spread spectrogram. The Doppler spread spectrogram is further processed downline using a multitask deep learning model, which utilizes ASL domain-specific knowledge in classifying the ASL sign. We utilize the phonological properties observed in the ASL language and encode them as auxiliary tasks. We utilize two auxiliary tasks. One is whether there is a repetitive motion present in the ASL sign or not. The second one is what is the moment type, whether it is perpendicular to the human body or parallel to the human body. These auxiliary tasks complement the main task and helps in it better performing the actual ASL gesture recognition. We evaluate the performance of mmASL using separate datasets for wake word recognition and ASL gesture recognition. The dataset includes close to 15,000 samples collected for 50 signs from close to 15 users. The dataset was collected from 3 different environments and includes several practical scenarios involving an interfering user. In wake word detection, we observed that the CNN-based deep learning model outperforms most of the traditional machine learning models. We note that the CNN-based algorithm can also perform well in several different environments wherein we have tested for the wake word. We note that Because of the difference in speed with which different users does the wake word, there is a small drop in performance in the wake word recognition for some users. We evaluate the performance of mmASL in gesture recognition by comparing it with several existing state-of-the-art systems like Kinect and camera-based solutions. The first thing is we observe that mmASL can offer comparable performance with existing state-of-the-art systems. We also note that the multitask deep learning architecture helps mmASL to perform better in different unseen scenarios involving an interfering user, also when it was evaluated on new untrained users. I would like to thank you all for listening to my talk. I will take any questions from here. Thank you.